All right, we'll cover some more statistics. Uh, there's one lecture out there on hazard ratios, odds ratios, basically stats for cohort studies, systematic reviews, meta-analyses. Correlations relate to that, but correlations can also be used in randomized control trials to kind of see what factors may have played more of a role in the outcome. Obviously, when we get to correlations, they aren't cause effect. Then we'll also get into t-tests and means tests. We won't get into analysis of variance, covariance, and those procedures, but just know that most randomized control trials will typically incorporate an ANOVA analysis of variance, which is an F-test, a means test, very similar to t-tests. Oftentimes there may be situations in which the p-value outcome from that means test is the same for a t-test as well as an f-test. But as you get more into research, if that's where the direction you want to go, which I think is a good thing, we need more good scientists, you'll learn more about that. So, correlations. They're not cause effect. They test relationships or associations between two variables. So you'll have something on the y-axis, something on the x-axis, and the correlation is designed to test the relationship between those two factors. It doesn't not cause effect. I mean, the example I use in class is I say it this way because I don't have the data, but the issue is there's probably a strong correlation, I say strong, correlation between shark bites, shark attacks, and ice cream sales in beach locations. And so they should be, why would that be? So you're saying the more ice cream we sell, the more shark bites there'll be? No, not saying that at all. Oh, the more shark attacks there are, the more we'll sell ice cream. Nope, not saying that at all. Saying that more ice cream is sold in the summer at the beach, and there's also more shark attacks in the summer at a beach. Therefore, there's probably a strong correlation between ice cream sales and shark attacks, even though they're not really related separately. I mean, that's just an example of why correlations aren't cause-effect and lack some of that rigor that way. Anyway, so here we have a near perfect relationship. Says it's perfect. Maybe there's a few things that may make it not quite so perfect, maybe round it up. Here's a 50% or a R value of 50, sorry, not 50%, or minus 50, plus 50, so downward slope is negative, upward slope is positive. In this case it's 85, so it's a little bit more along the line of regression, and then 0.15. So it measures the strength of linear association between two variables, so it's linear too. Key thing to keep in point. So one thing, this came up in one of the recent studies. It was the one pertaining to Dr. Ludwig and Dr. Hall's groups having some contention on Twitter with each other. And so what they had is, so let's assume these are all the data right here. And what you can see sometimes is this complete data set may be composed of 2 or more clumps of data. And so you could have a clump down here that clusters towards the bottom, and you may have a clump up here that clumps towards the top. When you look at the whole data set, this is what it would look like. And so sometimes when you tease out some of these groups within the total, the relationship diminishes. Because if you have clumps at the lower end of the XY axis and the upper ends of the XY axes, it will, so let's say we eliminate these. You'll have a cluster that's more like this and fewer points off the line than on the line. So anyway, so something to bear in mind, and that's also something to look for with associations. There may be other relationships within that, or other situations that, well, if you look at freshmen versus seniors, for example, in high school, you may have, and you're looking at height. So if height is along this axis, and then year of academic, 9th grade, 10th grade, 11th grade, 12th grade, or you could do age, and it's just the freshmen are here, seniors are here. And so while there may be, in high school, there may be a linear trend for an increase, and it may be associated within freshmen, maybe there's no association of height or seniors, but when you put them together, height tends to increase with age. So that's something to think about as well. So the coefficient of correlation can vary potentially infinitely, depending upon the x-axis, y-axis, etc. But the limits are a perfect relationship of 1 or minus 1, so an absolute value of 1, or to 0, and 0 is indicating no relationship. And so it goes from strong relationship at minus 1, no relationship, back to strong relationship, from minus 1 to plus 1, positive 1. The stronger the association, the further the coefficient is from 0, so that absolute value concept. So that's 0 being no effect. It is progressive, and so as you move away from 1, or as you move away from 0 on both sides of 0, the relationship becomes stronger, either negative or positive, depending upon how you look at that. If the R value or the association is 0 to 0.3, that's considered weak. 0.3 to 0.7, considered moderate, and 0.7 to perfect, high, or strong. It should always be qualified by the circumstances or nature of the variables. So this goes back to not cause-effect. So it's the ice cream shark correlation, and one doesn't necessarily dictate the other. So that's always where things kind of get muddy, is some people will either intentionally or unintentionally make an assumption that these things, one causes the other, but we also don't know the order of effect. Is it this leads to that outcome, or that outcome follows another outcome, vice versa, etc. Additionally, the squared correlation coefficient, R squared, so you take that 0.3, you square it, it becomes 9%. And so that squared correlation coefficient is called the coefficient of determination, indicating the proportion or percentage of variance in one variable that is explained from the knowledge of the second variable. And so height and age. And so if that relationship is 9%, so if 9% of one's height can be explained by age, so be it. And so how these things are determined, so 0.3 squared is 0.9%, or 0.09, sorry, 9% is weak. So if it's less than 10% weak, Less than 50%, 0.7 times 0.7 is 49%. Moderate, and then above 50%-ish, above 49%, 50% is considered high or strong. So that's kind of, now again, this percentage, this is math. There are some nuancy things, contextual things, and maybe weighting of things that don't necessarily make this exactly 9% if it's 0.3. But, for statistical purposes, that's kind of the outcome. So, for example, there may be counting things, and so our colors or known aspects, and it's the rolling the dice, flipping coins, colored beads. You deal with odds and those kinds of things, and so maybe there are some more law-abiding, that is, mathematical laws or scientific laws that allow that coefficient to be more true versus human factors. For example, you may have half of your population who might be composed of international students, and so that there may be some issues with international students compared to American students. That doesn't necessarily make that relationship or proportion or percentage true in all cases. So that's kind of probably more than I probably should say, but that's kind of my stance on using that R-squared value. It is used. I use it, but you also have to kind of understand some context to it and giving it some fluidity or flexibility. And it's not going to be an issue where it's, if the R value is 0.3, the R-squared value is 9%, where a quote-unquote true R-squared value would be 75%. And so it's probably going to be 10% or somewhere close to that 9%. So that's correlation. T-tests are tests of differences, and it's comparing the means. In this case, two groups. When you have a t-test, it's comparing two means. It could be from the same group, it could be from different groups. So here you have independent, unpaired samples. So a control group, treatment group, or we also have dependent or paired samples. So this would be you test something at the beginning and then something later or at the end to see what the change is in that one group. So that's the issue is the variance will likely be less if you have the same number of subjects in each of these groups. The variance will likely be less, assuming the same test. You're looking for the same thing, the same outcome. You're administering the same intervention, test, outcomes, things like that. Will likely be less in a dependent paired sample than an independent unpaired sample. The issue is these individuals serve as their own control. This is two completely different groups of people. And so you typically will need more people. You'll need to recruit more people for these using independent unpaired samples than you will with paired samples. And so an example I gave was in class was you're wanting to measure a fitness plan or a fitness program from corporate entities. So you have one from, I'm just saying this, I used in class, I'm not promoting any corporation, but if you have the one group of clients, customers from Genesis Health Systems or whatever the name of that corporation is versus Planet Fitness, and you want to see, so let's say you want to look at, they have a January enrollment membership issue, and then you want to see how successful people are at improving their health outcomes, whatever that health outcome is, in March, 3 months. So you'd have your control group your treatment group, or you'd have your two groups. You'd have your baseline at each, and then you'd compare the groups of each, Genesis and Planet Fitness, for change. How much change did they see in health over the course, and what you'll be looking at. So in essence, what you're doing is, so for all the Genesis people, you're looking at pre-post, and for all the Planet Fitness people, you're looking at pre-post. And then the difference is what goes here. That may be a complex thing to understand, but in essence, that's what you're kind of looking at. And so that's an example of how a t-test might be used to compare treatments. So the treatment or exercise condition, fitness condition, knowledge of their the complete program at one corporation versus the complete program, at another, can be tested that way with a t-test. And if there's no difference, that supports the null hypothesis. So if each group, so it didn't matter which gym they went to, null hypothesis. If one group had a different outcome, then it would support an alternative hypothesis. So if the hypothesis was one group will outperform another because of XYZ, then that would support the alternative hypothesis if that were true. Now, here's another issue for sample size. So N is your sample size, so it's the number of people in the study. As that sample size increases, the statistical power increases. Notice the means. So this is the null hypothesis mean, so the assumption is 100. Your assumption is both groups will have a score of 100. So using the Genesis Planet Fitness model, let's say over the course of the 3 months, let's say that their bench press, I know this is not, well, we'll say it's 100 kilograms. Make it sound a little bit better. So some people want to track bench press or squat, whatever, some metric. And so the assumption is they will both have a ending bench press of 100 kilograms. Well, you find out that one is 100 and one is 106. So the more people you would have in this study, the more likely you'd be able to see a difference than if it's low. So we'll wait for this to go back down. So statistical problem, it's at 100, it's very strong. However, as it goes back down, and as these bell-shaped curves overlap, all of a sudden, your power starts to decrease. And so, at very low numbers, it's very wide, and it's not likely different. So something to bear in mind, that this is a part of statistics I don't like, is that a lot of people will say, well, just increase your sample size. And it's like, if that were the case, you wouldn't need to increase your sample size. You could just do a study and then take those 10 subjects and then multiply their data 10 times to get 100, which doesn't necessarily come out to be true. And it's, in essence, you're filling in 90 data points with the same data, and so it's wrought with problems, and so it's not a true 100, and that's a problem I have with just increasing sample size. The assumption on this is everybody's going to be normal, your population will be normal. However, when you're dealing with 100 people, so use the United States, out of 300 plus million people, you're telling me the 100 people or the 10 people you pull out represent those 300 million? I say no. And so even if you had 100, there might be some issues with assuming that those 100 represent all 300 million. And so that's kind of a problem with this, as I see it professionally, with this just increase the sample size notion. But that's mathematically it holds. And again, the issue with health issues is it often isn't an issue of mathematics necessarily. It plays a role, but other aspects play a role too. So just bear that in mind. And then this last concept is the types of error. So we have a type 1 error, type 2 error. And this comes up most often, where this is most often used and looked at and scrutinized, is when you get into diagnostic. Where do you make a cutoff for saying somebody does or does not have a disease? Whether it's, I don't care if it's diabetes, cancer, whatever. And so there has to be something that you're looking for, an outcome, and there has to be a way to test that, to assess it. And so, the most recent example, and I was fortunate to be able to help with this, were COVID tests. And so for the state of Kansas, other states had similar processes. I was fortunate to help with COVID test analysis at the Topeka, the state lab in Topeka, when they initially were collecting COVID tests, when COVID tests took 3 to 5 to 7 days to get a test. So back in the February, March, April months of 2020, so before they had the rapid tests and the take-home tests, but they had to get through this process to get to those rapid tests, the take-home tests, etc., the more convenient tests, because it was a new virus, and so they had to go through these statistical processes to minimize type 1 and type 2 errors. And so an example of that is, so what is a type 1 error? So you may know the story about the boy who cried wolf. And if you don't know the story about the boy who cried wolf, very briefly, there's a boy who leaves a village, goes out, wanders in the woods on his own, and then he's young, he decides to get some attention, and so he cries, "Wolf, wolf, 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 there's a wolf." And the village people come out, and they don't see a wolf. And they're like, "Don't do that, don't." It's kind of like crying fire in a building. Don't cry fire in a building if there's no fire. And so he's, "Oh, I'm sorry, I won't do it again." And then next day, same thing, goes out and cries wolf again. No wolf. People come out. Now, we told you not to do that. Next time we're not going to come. If you need to make sure there's a wolf here. And then he says, okay. So the next time he goes out, and I guess I should say, he cries for help, but nobody comes. And so he ends up getting eaten by the wolf. And so the problem was, he made the mistake of, so there were too many times when he cried for help, but there wasn't a wolf. So there was too many type 1 errors. And so when there was a wolf, and he cried for help, they didn't come. And so those are just some examples of keeping straight the type 1, type 2 errors. So the other thing is, when you look at, so this beta number and the alpha number, that's omega, sorry. So the alpha's typically 0.05. The beta number is the type 2. And so what you want is a low type 1 and a low type 2. And that gets at precision, accuracy of that diagnostic. And so, one of the issues is, take them as you get more convenient, and this goes back to the whole notion of sample size. As you get more convenient and you have take-home tests, more people are involved, so your sample size goes up. And so that helps to have similar types of outcomes. And so there'll be more misses, more errors. That is, more people who may get tagged with COVID who don't have COVID, or people who don't have COVID but the test shows they do. But for the convenience, you're able to test more people. So anyway, so the example shows positive for COVID, but not present. That would be a type 1 error. Type 2 error would be doesn't show, so no wolf, doesn't show, but it is present. And so it looks like there's no COVID, and so your outcome of the test is your conclusion. So it's present or not, and then the disease condition. So if it's COVID or not, no COVID, COVID, that's your hypothesis. And so no COVID with a positive test is a type 1 error. COVID with a no positive test is a type 2 error. So the issue, so put that in perspective. I think also you see this with, I tend to use more kind of mortal conditions, and so somebody may get, so COVID, obviously COVID is not a fun thing to have, but when you get to some mortal conditions like terminal cancer, and you get a diagnosis or not of terminal cancer, that's going to change your mindset for the next series of months. And so let's say your physician, your oncologist, or the healthcare provider says, yeah, you have stage 4 terminal cancer, but maybe you don't. And so if they say that and you don't have it, you may get depressed, you may get all these things, but then come to find out, oh, I don't have it. Versus if the test says there's no cancer, but you do have cancer, and then the person dies in 3 months when they weren't supposed to have cancer, but then it was found out it was a mistake, then people are very upset, and it becomes very tragic in that regard. So that's how type 1, type 2 errors can be really life-changing in medicine, and why they try to minimize each of those types of errors, because neither one is wanted. So hope that makes sense, and let me know. I will post the assignments, I'll say this week. This is mid-February, and so it'll go out. So you'll have, my goal is to give everybody kind of 3 to 4 weeks to get all the projects done for the rest of the semester. Remember, this is a 2-hour class, and it ends at halfway through the semester, ends at 8 weeks, and so we're just over 4 weeks heading into the 5th week, and so I'll post those assignments later this week, and then we'll go over them in an upcoming video. Thanks. Have a great rest of your week, and see you next time.